Good morning, everybody.
Good morning.
Oh, word of the day. Crap. Got to think of one before Robertson comes on. Yeah, there he is. Crap. All right, give me a second. Oof. There we go. Ultramafic. There you go. I think that's a pretty good one. It's of igneous vine rock. I don't know if you've heard of this word. It's a portmanteau.
Good word, that.
There you go. It's a portmanteau of magnesium and ferric, mafic. And yeah, it's not like a super fun. Hello, Jimmy. See you without a hat on. That's rather, I don't know, disconcerting. Where was I at? Super cool. All right, so let's get busy. And today we're going to be talking about Europa and Ganymede. Ganymede is always a little bit of a kind of add-on, in terms of, super sexy sisters. Europa kind of gets the prize every time. That's where most astrobiologists' eyes are focused. But Ganymede is also really interesting as well. So if you remember, let's kind of skip ahead here. If you're really, bored and need of something to do, you can watch the, what the fuck's his name? Shit, I forgot his name. I've watched that film so many bloody times. Anyway, the Snowman's song. Can't remember his name off the top of my head. Someone's going to remind me. Where's the Olaf? There you go. Thank you. That's the one. Yeah. I knew there'd be at least like half of the class who have small female relatives who force them to watch that over and over again. Anyway, so let's get back here. So if you remember, let's move this out of the way. Let's go over there.
I smell food.
Who is that?
Oh my god.
Hello?
Waffles.
Is that you, Angela?
Oh my god. You guys can hear me.
Or is
Waffles is the name of my dog.
Waffles? Oh, there's Robertson. Hello, Robertson.
It's my dog. We just
are you muffled because you have a cat on your face, Angela?
Yes.
Oh, okay. That must be uncomfortable. Did you have a question, or you just?
No, I just got out of bed.
Oh, okay, cool, nice. No commuting time, right, for online classes? I think that's pretty awesome. Anyway, so if you look, let's blow this up a little bit. Stick it back to what it was before. There you go. So it's kind of a little bit weird because we usually do it the other way around with the moons on the right. Anyway, so not to scale in either distance or size, but this is just a refresher of the order of those moons. And the kind of the really neat thing in a sense is we've talked a lot about habitable zones around stars, and we'll talk a lot about those when we get to exoplanets. And, you know, obviously that Earth is bang in the middle of the habitable zone for our star, and Venus and Mars are kind of on the you know, either edge essentially. If you think about habitable zones around Jupiter, which is a little bit weird because it's a planet, right? It's not a star. It doesn't produce heat like the sun does, but it kind of does through its gravitational effects. Ganymede and Europa are very much in the middle of that habitable zone, right? So if you think about Jupiter as a kind of like almost a little mini solar system, Europa and Ganymede are right smack in the middle of that habitable zone. Io, not so much because it's massively volcanic. Also is permanently inside the radiation field of Jupiter. And Callisto is too far out, it's too cold. Pardon me. So Europa and Ganymede are kind of where it's at, really. Okay. And as always, stick your hand up and shout if you've got questions. I'm going to try and bring the chat up so I can keep seeing that. Wherever the hell that. Zoom is cool, but oh, don't apologize for laughing, Robertson. It's fabulous. Just means I know exactly who it is that's laughing because you have such a distinctive laugh. That's all. Let's stick that up there. Can you quit that? All right, stick that there then, so I can see stuff pop up. Anyway, where am I at? So a little bit of overlap, obviously, with the lecture on Jovian moons in general and also on Io. But obviously, Galileo and the Hubble missions have been the ones that have given us the most information. The Voyager and Pioneer flybys were pretty much just a blink of an eye kind of view, and they didn't really get lots of good information about the moons, whereas Galileo really did. It spent a long time there. And one of the very first observations of Europa, which got everybody excited, is this one here. It looks a little bit like, I don't know if anyone's seen the film Pixels. Is it Pixels? Yeah. Which is actually pretty cool. I like that film. But anyway, it looks a little bit like that, right? So if you look at the picture on the right that I'm circling, that heavily pixelated stuff, right? And this is just, I don't know why it's heavily pixelated. Hubble was a fabulous telescope and Europa isn't that far away. But anyway, that's most likely water, right? So that was what really kind of kicked off all the excitement of the Galileo mission, which Galileo actually launched, what is it, about a year before Hubble did, but it took over 6 years to get there, right? So Hubble had already kind of seen this stuff before Galileo had gone into orbit around Jupiter. Anyway, so a little bit of just a bit of information, kind of an old style image here. Both Europa and Ganymede, spelling mistake, have an oxygen atmosphere. And I obviously couldn't spell when I wrote this. There you go, that's better. And it's produced by the interaction of those moons with the radiation field of Jupiter. So basically, the radiation or the kind of charged ionosphere, essentially, of Jupiter strip oxygen off of water. Right? So hydrolysis of water. And so then hydrogen leaves and oxygen kind of gets left behind. But that's not the really interesting stuff. The really interesting stuff are two things. One is I'm gonna see if I can move this over a little bit. There you go. That's a bit better. You can see stuff. One is the surface of Europa and Ganymede, because that is a reflection on what's going on underneath. And two is the possibility of oceans, right? And so as you remember kind of early on, really what we care about is water, right? Because as far as we know, and we don't have any proof to the contrary, water equals life, at least on Earth. No water, no life. Okay, so these next couple of slides are going to be really side-by-side comparisons of Europa and Ganymede. So Europa is on the left, Ganymede's on the right. Don't forget as well that Europa is in the middle of that orbital resonance deal, right? So it is not heated as much as Io is, but it is heated more than Ganymede is. And that really is what creates the difference in their surfaces, and also potentially in what's underneath the surface, right? So don't get any impression that these places are going to be habitable on their surfaces, right? They're both extraordinarily cold and have very little atmosphere and are bombarded by radiation from Jupiter, right? So they are not kind of places you'd want to go holiday on the surface, at least. But if you look at the surface, and just in general, like a kind of overview, Europa is very smooth. It's not as smooth as Io, which is like a baby's bottom, basically, or rather perhaps a teenager's bottom with the pimples. But it's smooth, and it has all these lines going over it, right? And the very rare crater, you can see one down on the bottom right. I forgot what its name is, right? So that's it. And bombardment is almost certainly constant in the Jovian system. Blue gunk, Vivian. So the blue is ice. It's the brownish kind of reddish gunk is they're most likely things like tholins, which you see on the surface of Pluto. So they're kind of organic chemicals which either were produced by Europa itself and then kind of fall back down onto the surface, or perhaps even get expelled into the orbit and then kind of smack Europa as it kind of goes around Jupiter. Or they've been deposited by meteoroid impacts. Oh, the pixelated blue bits. Okay, that's water. Almost certainly. Yep. Actually, let's skip ahead. Hey, who needs to keep to a particular format? Let's see, is this one? So forget these pictures down here. If you look at this image, can you see those bits at the bottom? They kind of like look, I don't know, look like gas escaping from a balloon almost. Those are water jets. Well, not water jets. They're kind of equivalent of like water volcanoes, I guess, right? So there's sufficient liquid water inside Europa and sufficient pressure and energy to force that water vapor out into space, into orbit around Jupiter. And in fact, Jupiter has, let's see, there we go. Give me a second, Angela, I'll just get back to that. Jupiter has rings. In fact, all of the outer giants have rings. It just happens that Saturn's are, you know, kind of prettier and more definite. But Jupiter has a pretty large ring system, and a lot of that is stuff that's been ejected from Europa. Oh, okay. So getting back to Angela, yes, that picture's pixelated. Hang on, get you back. Most likely because of the resolution of the Hubble Space Telescope at that distance and size was fairly poor. Right, so don't forget this is a camera pointing, I don't know how many, what would that be? How many million miles is it from? It's like 90 million miles from here to the sun, which is 1 AU, and Jupiter's 5 AU, so that would be 4 times that. What's that? 360 million miles away, right? So it's a long way away. Yes, it does. So back to Vivian. Essentially, that's what we're going to talk about for mostly the rest of the lecture. And we'll get there. Just hang on a sec. If we bounce around too much, I might forget important stuff. So getting back here. So again, if you, these cracks, right, essentially that seems to reflect some kind of ice turnover and ice movement, right? So this isn't a static frozen ball of ice. There has to be an ocean underneath that, or at least different kinds of ice which are more mobile, right? I don't know if, sorry, anyone have a question? If you got a question, just shout your name out and ask it. I really don't mind. That's totally fine. You don't have to do it through the chat. In fact, sometimes, crap it, where's the chat gone now? It's a royal pain in the backside, to be honest. There we go. So, where was I at? Yes, hello, love. There's all kinds of different types of ice, right? So on Earth, we pretty much only see one type, I think, maybe two. Elsewhere in the solar system, there are different combinations of pressure and temperature which produce different types of ice, right? And types of ice which are harder and stronger than steel, for example, right? So, you know, ice is hard, obviously, but these other types of ice are very different. So there's lots of different types of ice. Anyway, that's kind of a digression. If you look at these two pictures, you can also see that Ganymede on the right, it's kind of between Europa and Callisto. So this is Callisto over here, right? On the far left, it's not in orbital resonance. It doesn't have really tidal heating. And it has so many craters on it that any new creators most likely erase more creators than they create, right? So it is the most heavily cratered object in the solar system. Io is the most volcanically active object in the solar system. So Jupiter kind of wins a lot of prizes, really. And Ganymede is between Europa, which has a very smooth surface, no or very few impact craters, and Ganymede, which is all impact craters, right? And not Ganymede, Callisto, which is all impact craters. And so it's kind of in the middle. Let's see where we're at. And so you have regions that are very smooth, and then regions which are very, very old and very heavily impacted. Pardon me. And if you look at it closer up here, let's just pull this up a little bit. Make sure I'm not missing anything. Let's put that back. There we go. If you look at it here, you know, this is a close-up picture taken by the Galileo probe of the surface of Europa, and so you can see these cracks, right? And there's pictures that are even at higher resolution than that, and they really look like kind of like expansion cracks in ice. You know, ice that is kind of swelled up and then kind of collapse back down, and it cracks along those lines. And you can also see some, they're not kind of, let's blow this up a little bit. Right, a little bit pixelated, but these features here, these kind of pimples, those are called lenticuli, right? And they're thought to be areas of like softer ice that have more heat underneath them. I'll fix that later. Now, if you look at Ganymede, right? Now you have something kind of in between, right? So you're on the right-hand side here. Hopefully everybody can see what I'm pointing at. On the right-hand side here, you can see it's, you know, it's very smooth, very few craters. So this is relatively new material, right? So essentially the age of the material can be determined by how many craters it has on it, essentially. And this one has very few. You can actually even see like a little central ejector pimple in that crater, which is kind of cool. However, there's also large swathes of really old material on Ganymede. And so this stuff over on the left, you know, you can see it's essentially nothing but overlapping craters, right? And so this surface on the left of this image is thought to be around 4 billion years old, right? Now, if you compare that to most of the Earth's crust, which is around 100, 150 million years old, this is far, far, far older. And that basically reflects the heat within the moon itself, right? And so, Vivian, this is really what gets to your question.
Alexa, set a reminder at 3 p.m. to call Gabriella.
Okay.
I'll remind you at 3 p.m.
Do you want me to remind you at 3 p.m.? I can. I don't mind. That's all right. I think someone last time had like a message from UPS telling them that their delivery had been cancelled or something. Thankfully, most of my family's asleep, so, or in bed at least, so I don't have many distractions going on. Anyway, if you hang around a little bit, maybe you'll see my dog come down. She's being a teenager and sleeping in bed at the moment. So what this all results in, or reflects rather, is the almost certainty that Europa and Ganymede have oceans, right? And so this is probably one of the most exciting discoveries in astrobiology ever. Probably ranks alongside the discovery of the first exoplanet back in, when was that? The mid-90s, I think, right? So it's hard to overstate how important this discovery is, because if there's, you know, if there's water, then there's a good chance that there's also life as well. And the problem is that we don't really know what these things look like under the surface, right? We can infer, and there's lots of different ways we can do that inference. So, for example, let me just have some water. Here on the Ganymede on the right, Ganymede is the largest moon in the solar system. And Ganymede is actually larger than Mercury, right? So it's about 8% larger than Mercury and less than half of its density. However, we also know that Ganymede has a weak magnetic field like the Earth does, right? So from that, we know that the only way you're going to get a magnetic field is if you have a liquid iron core within that moon rotating, right? We don't know what causes a magnetic field on Jupiter, like some kind of massive metallic hydrogen core, we think. But on Ganymede, it's a rocky iron or iron sulfide core, right, which is rotating within its mantle, just the same as on Earth, right? So Ganymede and Earth in some ways are very similar. However, if we know that the density of Ganymede is less than half that of Mercury, yet the center of it is made up of very heavy, dense stuff, rock and iron, then the rest of it must be really light stuff, right, to make up that kind of low density moon. And the only thing really that explains that lower density would be water and ice. Right, so even though we don't have any ejector or you know, kind of water vapor spewing out of Ganymede, the fact that it has a magnetic field and an iron core, yet is half the density of Mercury, while being larger than it, means that it has to have a water ocean, a saltwater ocean around the that underneath that icy surface and around that rocky mantle. What exactly that looks like, we don't know. This is basically our best guess, right? The only really way of figuring stuff out like that is a subsequent mission later on, which is hopefully happening in a couple of years. So it's not going to be nitrogen, Jimmy. So a question from Jimmy about what type of seas it could be. So let me kind of gather my thoughts. It's not going to be nitrogen because it's not cold enough, essentially. You have to go an awful lot further out in the solar system to get those lighter elements. So it was Pluto that had nitrogen ice. So yeah, that's kind of one reason. Second reason is that it's basically too warm, right? So both too warm in terms of the position of Jupiter within the solar system. So you tend to find because it's just outside the frost line. So essentially you're going to find still a lot of water, basically. And then the much lighter gases, hydrogen and nitrogen, are going to be a lot further out of the solar system, basically because they've been blown there by the solar wind. That's kind of the current theory. As to it being water vapor, I don't actually know the answer to that. It just seems to be kind of like one of those assumed things. You know, everybody says it's water vapor, so it must be. I don't actually know. Trying to think of a good answer. I don't actually know. I think it's from the visible spectrum recorded, but I don't know where that information would have come from. Can't have been from the Hubble Space Telescope, because that's in the wrong position to be able to get any kind of light spectra. And I'm not sure whether Galileo had that kind of instrument. I don't know. I'll have a look into it. I'll see if I can figure out how they determined that it was water. I've just always just got. They all said it is, so you know, you kind of take that at face value. However, we do know that it's salty. How do I get this back moved away? Go over here. Zoom is both awesome and pain in the ass sometimes, to be honest. All right, stick that back over there. So where are we at? Let's find the nice areas. We'll get back to this in a little second because we haven't really gone through what Europa looks like yet. So this is actually a really cool experiment, and it wasn't intentional. So essentially, the Galileo probe had what's called a magnetometer, which is able to detect magnetic flux lines, right? And if we quickly scooch back here, you can see that Europa is orbiting Jupiter within those magnetic field lines, right? They're a lot further out than Io, so it's a lot less heavily affected, but it's still there. And so essentially what, I can't remember where these scientists were from. I think they might have from Russia or I'm not really sure, can't remember. Anyway, what they did was they looked back at a whole bunch of data from the magnetometer going around as it passed by Europa, sorry. And this is like an artist representation. And so they wondered whether, you know, if we're able to look at the magnetic field lines, and if there are water vapor jets coming out of Europa, if those jets have ions in them, right, so like salt water, then they should cause a perturbation in that magnetic field, right? Just because essentially it's like an electric charge, you know, it's like how motors work, you know. And so what they did was they went and looked back at all this, you know, huge amount of old data that no one had really thought about looking at. And they actually detected a blip in the magnetic field of Jupiter as Europa passed through it and ejected some water vapor out from underneath its crust. And so from that, we know that it's a salt water ocean, which also kind of makes sense because salt lowers the melting point of water. And so even though these are warm places, they're not like super toasty. And so it's almost certain that these undersurface oceans are liquid or less frozen, at least, because they contain ions. Don't know what kind of ions, but we know that they contain some kind of ions. Okay, so Vivian, this is a very long-winded way of getting around back to your question. So the reason why that water comes out is basically the Io is constantly being, not Io, Europa is constantly being squeezed and flexed, right? So it gets warm, but also it means that its surface is constantly flexing, right? And if you have something that's brittle and rigid and you constantly flex it, it's going to crack, right? And so that's essentially what these all these cracks that cover the surface of Europa are from. And there's actually, the next mission is going to be measuring how high those that ice moves. Let's see what the difference in. Oh, there you go. So I can remember the numbers. So this future mission to Europa is essentially going to be measuring how, let's go to this one instead, how much the tidal flexing of Europa, how high that surface rises. And because solid material is affected less than liquid material, right? If it's solid underneath the surface, which we don't think it is, but it'd be nice to have, you know, to know. If it's solid on the surface, the tidal flexing will cause Europa to do this, right? It's going to flex outwards, you know, around 3 feet, right? Which is, you know, a very small tide on Earth, right? Now, if it's a liquid ocean underneath, then that water is much more likely to be affected by gravity, much like spring tides on Earth are, right, affected by the moon. And so that movement is going to be much larger. It can be up to about 100 feet by their calculations. And there are all kinds of like crazy physicist calculations involved in that I don't understand. I did actually learn them once, but I don't know. Here's another, actually, got another word for Robert in. You can look this up because I can't remember exactly what the definition of it. There you go. I think that's spelled right, not 100% sure. Basically, it's how to measure thickness of ice by its deflection under weight. And that's all I remember of it. Very interesting. Don't understand it. Far too much math for my liking. Anyway, so essentially, if you've got a constantly squeezed warm ball of rock and ice, you have a brittle, crack-prone surface which is constantly being flexed. Then, and you're going to have, as a result of that internal heat, water circulating, or at least warm ice circulating in that subsurface ocean. then you're going to get stuff escaping, right? It's simple. It's not gonna hang around, right? And so almost certainly there are going to be, get out of it, regions underneath this crust which are warmer than others for whatever reason. And it's most likely that those regions are the ones where you see those plumes of water vapor. Also, I can't quite remember off the top of my head the course, but when we get to Saturn, which will be next week, I'll have to double check the schedule, and look at Enceladus. That has particular events on the southern pole of the moon. Can't remember off the top of my head why, but presumably because of some kind of, not necessarily tectonic activity, because that applies to plates of rock moving around on a liquid mantle, right? So that doesn't apply here, but certainly constantly being flexed like so is going to both keep that water warm and also create cracks in the surface, which will cause that water to leak out, basically. So that's why there are these water plumes emerging from Europa. Basically, that's the long way round of answering that question. So there's a couple of things which future missions, well, let's say 3 things, are really, really, really interested in. One is proving whether or not there are liquid oceans under the surface, right? That is super, super important, because an awful lot of theories about what those moons look like are based on that hypothesis. The second thing is, how thick is that ice, right? And so these models are guesses. That's it. We don't know, right? It's very difficult to know this kind of stuff. And the Galileo probe, essentially, it discovered that this was the case. And so because of that, it didn't have the measurement, the tools to follow up that, because basically when you launch a probe, it's like, well, I think we're going to find X, Y, and Z, so we're just going to send it off like so. And then if you find A, then probe's already gone. 6 years later, you're doing the science. And so it's the next probe then gets built with those instruments to measure those things. Very much the same way as all the rovers on Mars are essentially incremental improvements based on the discoveries that the previous ones made. So how is there an ocean? How thick is the ice, right? Because kind of dictates, how easy is it for stuff to get out, and how easy is it for us to find out whether there's life there or not. And the second one is, if you look at this image here on the left of Europa, does that water come into contact with the mantle, right? The rocky mantle. That is super, super important. So here you see on Ganymede, they think there's this, I think it's tetragonal ice, or ice 6, so a funky kind of ice. They don't think that the water is in contact with the mantle, and that matters a lot because of the potential for hydrothermal vents. So if that rocky core is constantly being squeezed and flexed, there's a good chance that energy is able to escape, thermal energy is able to escape in the form of these kind of hot plumes like you find around hydrothermal vents. And given that we know how much life exists around hydrothermal vents on Earth, then that's about as exciting as it gets, in terms of astrobiology. If there are analogous systems on Europa, then that's a very big increase in the chance of finding life somewhere other than on Earth, right? And that would be around those hydrothermal vents. Now, it's not a guarantee that there are hydrothermal vents, right? Because these on Earth are due to tectonic activity, right, and cycling of material within the mantle of, or really the lithosphere of the Earth, right, and then the mantle underneath that. But there are other ways in which you can have really warm environments, and obviously there's radiation that can provide energy, but also there's, here we go, mafic. Right, so there's a process called serpentinization, which is the creation of serpentinite, which is a mineral, which is essentially a what is it? A hydrous magnesium silicate, right? And basically, it's something that happens on Earth as rock is cycled back up to the surface of the crust. Essentially, it's a particular type of rock, like olivine, and then you add salt water, and that essentially sets off an exothermic reaction where that rock turns into a different type of rock, right, called serpentinite. And so that produces a huge amount of heat, right? And if that cycling is occurring on the seafloor of Europa, then there's a very good chance that that will produce enough energy to essentially create an analogous environment to a hydrothermal vent, right? Not necessarily the same kind of output of, you know, electron-rich donors, but certainly it'll be enough to provide the heat. And so one of the things that a future mission also wants to determine is how much of that material from down here on the seafloor, if there is actually a seafloor, right, as opposed to a layer of ice here, how much of that material on the seafloor circulates up through that ocean or warm convecting ice and then gets spat out of those vents on the surface of Europa, right? So the hope is that by sampling some of those ejecta, scientists will be able to figure out what exactly the nature is of that surface floor. And obviously they'll be able to confirm you know, what type of water it is, you know, and so on and so forth. So essentially these two moons, and Ganymede is has always been a little bit less studied because it's less hot, but it's no less interesting, right? And the fact that there are clearly areas of rapid ice turnover, right, where it's obviously a lot warmer, and areas where it isn't, is also super interesting. Kind of makes you wonder if it's like there are, you know, kind of some kind of subsurface geology, right, in terms of, or geography even, in terms of like mountain ranges or something. And you know, the smoother parts are basically where there are oceans just underneath the surface. You know, it's, I don't know. So kind of one of the top priorities in astrobiology is really going back to Jupiter and carrying with it the tools to be able to figure out, you know, what those oceans look like and what's in them, and how thick they are and things like that. So hopefully that's going to shoot off in the 2020s. There was supposed to be a mission to Mars this year. It's going to be next year. I think it's around 2022 or 2023. NASA's hoping to send a new probe to Europa. But the planning involved, the timescales involved in those missions are quite hard to comprehend, right? They get planned a very long way ahead of time, and then they tend to last for an astonishing amount of time. I think Galileo, it got punted into Jupiter in 2003. So including travel time, that's what, 14 years, right? So it took 6 years to get there. So that was 8 years that probe spent whizzing around the Jovian system taking measurements. So these things last for a long time. So it's really very much a guessing game on the part of NASA scientists, or world scientists, to think what measurements do I want to take, and what might I want to take in 15 years time, right? Because once those probes have been sent off, you can't just bring them back and tweak them. Anyway, so that's pretty much it for Europa and Ganymede. Europa really is the hot sauce when it comes to astrobiology. It's the most, well, one of two, because Enceladus is really the other one, most exciting places to look for life outside of Earth, right? Anywhere, essentially. And it's a long way away, but it's not so far away that you can't get there in terms of probes. Obviously, sending people there is, yeah, that's not going to happen for a good long while. If you think that it takes, it would take probably a couple of years to send people, to get people to Mars. I think, how long does it take to get to Mars? Maybe 6 months if you're kind of pushing it a bit. And that's what, 45 million miles away, whereas Jupiter is about 350, 400 million miles, so it'd take a lot longer. Anyway, that's pretty much it from me. Does anybody have any questions about any of that stuff? Oh, hang on a sec. People did have questions, I just wasn't paying attention. Sorry, that thing disappears a lot. Let's get back. Mariah, I believe so. Yes, it was because of the virus. They weren't able to get everything together and get that launch out in time, because essentially every time we launch a probe, probes are really heavy, and so they can't carry a lot of fuel, because the more fuel you carry, the smaller the probe has to be. And so typically probes that get sent into the outer solar system get sent with what are called gravity assists. And so they send them out, and then they get a boost around Venus or the sun or Earth. And that's actually how Galileo did its observations of Earth. It was on a gravity assist past Earth. And so there are usually particular windows, launch windows, in which everything lines up well enough. And I think with all of the craziness was going on, was they basically missed that window. And so the next one is going to be in another year or two. Kiara, that's a funny question. That's absolutely terrible idea. And in fact, that's actually why the Galileo probe was forced to crash into the upper atmosphere of Jupiter. How long did it last for? There's actually, I'll have to dig out, on Netflix, there's a really cool video about, what is it? No, that's Cassini. Sorry, getting my wires crossed between Galileo and Cassini. There's actually a huge amount of effort that goes into preventing any contamination of extraterrestrial environments with anything from Earth, right? So when you see those people wandering around in hazmat suits and stuff when they're working on space probes, it's not because they want to protect the probe, it's because they don't want to shed microbes onto them. And so there's an incredible amount of effort involved in preventing the contamination of extraterrestrial environments with microbes from Earth, because we just don't know what's there. And also, if we want to look for life, it doesn't make sense to bring life with you, because then you've kind of found it, right? So no, they're most definitely not going to do that. Yeah, Kiara, you could go there. It'd be very, very lonely. No, Kiara's not going to out-evolve us and come back to take over. All right. Okay. So let's just focus on the serious questions, huh, Jimmy? Anyway, actually, it wasn't Jimmy's fault. It was Kiara. I'll blame her. So.
Wait, why I getting on the blame?
Yeah. Anyway, to answer to Pedro, there will be a study guide. Haven't done it yet. It's next on the list of things to do today. Essentially, I just haven't kept up on that like I did at the beginning of the semester. Also, it was only the first 2 classes that I couldn't see your Zoom presentation slides. Oh, right. So,
Yeah, that's sorry.
yeah, Pedro, I'm gonna have to. Shit. So I'll have to figure out a way of putting those on Dropbox and then sending a link out to the class, because I can't put them on Blackboard. I don't have the storage space. So the problem with Blackboard is that they give us like that much storage space, and they haven't updated it, even though everybody's doing, you know, online classes and stuff. So their advice was, well, you know, you could put it on like Google Cloud or something. And so I've got to figure out how to do that, because I had to take them off to be able to upload the last one. So essentially all of these videos, I only have enough for a week's worth on Blackboard, because otherwise I run out of space and it won't let me upload them. So I have to delete stuff. So that'll be the next thing. And then the second thing will be the study guide. I'll figure out how to get that up. All right, what else?
Thanks.
No worries. Well, no, actually, again, to Jimmy, you know, the whole panlithospermia kind of idea. I don't know if you saw the desiccation resistance PowerPoint. Don't know if I've got it up. Where are we at? Which one was that? Shoot, which one was that called? There we go, Xerophiles. So check out the Xerophiles PowerPoint, Jimmy, and you'll see that. There we go. Where do I get back to what I was on? There we go. Yeah, the Xerophiles PowerPoint actually has some neat pictures of lichen that they stuck to the outside of the International Space Station and left it there for 1.5 years, and it was fine. So so yeah, why don't I do it on Google Slides? Oh, post them on YouTube. That's like, Sam, that's like technology and stuff. I'll have a look into it. I'm not a very technologically savvy person, so
Dr. Andrews puts up his lectures up on YouTube, so if you need help, you can always ask him.
well, if Dr. Andrews could do it for me, that would be fabulous. But I've got a feeling that he'll tell me some things. Probably beginning with please and ending with off. Yeah, I can ask Bob as well. I know that he's got his own like private YouTube channel, and I have actually twice uploaded a video to YouTube. So technically, I know how to do it. I need to figure it out. So yeah, I'll look into all of that, because obviously putting them up on Blackboard isn't a very good solution, I don't think. So yeah, I'll give that a shot. I'll look into that today, because I think that would be a pretty neat solution. It certainly wouldn't be any more effort than the hoops that I have to jump through to get them up on Blackboard. So it won't be the loves. No, Jimmy, you're not going to live forever. Sorry, man. Hope to break the bad news to you. Anyway, yeah. So I'll check out uploading these things to YouTube. Oh, oh well, maybe. Who knows? I'll check out uploading all these things to YouTube, and I'll also get on top of the study guide too. Those are 2 things, as well as writing the quiz for next Monday, that I need to get done today. As soon as I've got the quiz up and kind of ready, I will let you know the details of it, and then it will be during class period on Monday. So starting at 9 a.m. Unless you have any particular reason why you can't make that, and I'm pretty open to reasons. You know, if you've got you know, work schedules are crazy, or you know, extremely loud snoring dogs in the morning or something, well, it doesn't really matter. Then I'll make sure I can get that scheduled so that you can take it at a different time. Not particularly bothered by that. Not sure how to do that, but I've been told that it is possible.
Is the quiz on the 6th or the 13th?
I don't know. What's the day next Monday?
This upcoming Monday is the 6th.
Yeah, pretty sure it's next Monday. Let's check the schedule.
Right.
Yep, it's on the 6th.
Awesome.
Hey, where's Enceladus? Shit, I forgot it. All right. Titan and Enceladus. Can't forget Enceladus. And then we've got to put, sorry, here you go, real-time schedule changing. I'll post that up again. All right, that's like, what, 4th on the list? Shit, you guys kind of keep me busy. All right. Where are we at now? No, I don't want that. There we go. Cool. All right, everybody. So I've obviously got more than enough stuff to do in the meantime. I'll, straight after I've had my coffee, I'll check out YouTube and uploading those videos. Might give Dr. Sheldon a call to see how he does it. And that's pretty much it. So as soon as I've got all this stuff up and running, I will send out an announcement, and obviously with details and stuff like that. So you'll be able to check it out for yourselves. I think that's about it for me. Anybody else have any other questions? Nope. All right. Thanks very much, everybody. It was a lot of fun. Kiara, thank you for your input. It's always a pleasure.
Wonderful. Have a good day. Have a good weekend.
You too, everybody. Take care.
See ya.